So last time I introduced the Kodaira dimension of a smooth algebraic variety, which was defined in terms of the rate of growth of the space of sections of the canonical bundle and its multiples. It was a particular case of the Itaka dimension for an arbitrary line bundle. And in particular, we saw what the Kodaira dimension of various curves are. So if so this is basically P1, this is basically an elliptic curve, and this is other curves. And we want to see to what extent this birational invariant that we attach to a variety enables us to distinguish varieties which are in some sense have something to do with P1 from varieties which in some sense have something to do with E, or maybe those of general type, namely where the Kodaira dimension equals the dimension, which are more like curves of higher genus. It may be something in between. And since this is an arithmetic geometry workshop, well, we'd like to know what it says about the arithmetic of these varieties. But for the time being, let's do a little bit of geometry, of birational geometry, and study just a little bit about the behavior of this thing. In one of the exercises, it's called easy subadditivity. So notice this additivity in products. You can ask, what about varieties which are not exactly products, but are fibered? Well, you can't say an exact thing in this situation, because you can fiber up to birational equivalence. You can fiber any variety over P1. So in some sense, the base is you can fiber over P1 and in fact you can fiber it over P1 with fibers which are of general type. But what you have is an inequality. So if the fibers, this is the generic fiber X eta B. So I should draw the picture. I have my X, and it maps to B, and here I have the generic point, and here I have X eta B. And so the Kodaira dimension of, so what this says is if you lost something, if the generic fiber is not of general type, so there's some defect in terms of Kodaira dimension, then the same defect at least will occur in the variety in the total space. A particularly important case is when the fiber is P1 or something like P1. So here's a definition. We say that a variety is uniruled if there is a variety B of dimension 1 less and a dominant rational map B cross P1 to X. So this is not exactly fibration on X, but at least we have something which is fibered by P1s and a dominant rational map. Well, this might be just a rational map, but everything is birational equivalent. So that's a uniruled variety. By what we have here, or in fact the additivity there, if you have any variety, B cross P1 will always have Kodaira dimension minus infinity. Another thing that is easy to see is, well, since this is dimension n minus 1, well, this is a dominant rational map. This means that this is of the same dimension. So this is generically finite. And it's easy to see that the Kodaira dimension, if you take a generically finite cover, the Kodaira dimension can only grow, because any differential form here pulls back to a differential form here. So the space of differentials only grows. So if this has Kodaira dimension minus infinity, this must have Kodaira dimension minus infinity. This is what, so if your variety is covered by P1s, this is what this says. If your variety is covered by P1s, then the Kodaira dimension has to be minus infinity. And the converse is an important conjecture, sometimes called the minus infinity conjecture. I forget to whom one should attribute it, but maybe in the final notes I will find it. So it follows from the existence of good minimal models. It's part of the sufficiently enlarged minimal model program, which I will discuss later in this course. And the conjecture is that this is an if and only if. The only way a variety can fail to have any differential forms whatsoever, canonical and pluricanonical differential forms whatsoever, is if it's covered by rational curves. Yes?
I think Mori attributes
Mori attributes it
it to Mumford.
to Mumford. Okay, so maybe Mumford-Mori conjecture. Anyway, minus infinity conjecture is a good name because then you remember what it's about. The only trouble is that we don't give credit this way to the right people. So we are basically, okay, so here's what happens with surfaces, which really explains why general type is called general type. For surfaces, we can completely classify the varieties which are the surfaces which are not of general type. So I'll add here 2, Kodaira dimension 2, general type. It just means it's too crazy to classify. People have been working for decades trying to say something about what can happen. What are the things that can and cannot happen in the zoo of surfaces of general type? But surfaces not of general type are completely classified up to birational equivalence. So any surface of Kodaira dimension minus infinity is covered by P1. So the conjecture stated there is true for surfaces. It's also true for threefolds, but that's a much harder result. But no, this is up to birational equivalence. So these are these are either rational or ruled surfaces over some curve. Kodaira dimension 0 is a collection of situations. Each one is fairly explicitly understood. Abelian surfaces, they are parameterized by a countable collection of moduli spaces. By elliptic surfaces, these are quotient. I think they have been mentioned somewhere. I forget whose lecture. Say again? Harari's. So bielliptic surfaces are surfaces that are quotients of products of two elliptic surfaces by an exotic automorphism group. I'll give you an example that is very important later on. K3 surfaces are a collection of surfaces that have very interesting geometry, and you can spend a lifetime studying K3 surfaces. And Enriquez surfaces are certain quotients of K3 surfaces by a certain type of involution. And Kodaira dimension 1, I wrote here many elliptic surfaces. By that additivity, if the dimension of the base is 1 and the dimension of the fiber and the Kodaira dimension of the fiber is 0, namely the fiber is an elliptic curve, then the Kodaira dimension is at most 1. And in fact, it can be minus infinity, it can be 0, it can be 1. And the cases in which it's 1 are... So every surface of Kodaira dimension 1 is an elliptic surface, is a surface fibered by elliptic curves. Okay. I need this. So I'm going to mention a few things that I think were covered by Hassett and by Starr last week. Wait, I'm a bit confused. So I want to now analyze the types of varieties that can occur, at least in terms of the Kodaira dimension, at least roughly. So the first things, according to the conjecture that I just removed, the first thing that I want to understand is the minus infinity case. And by the conjecture, these minus infinity cases are covered by rational curves. So they have something to do with rational curves. And I would like to see to what. So the goal is to break a variety of Kodaira dimension minus infinity into two pieces. One is everything that has to do with rational curves, and the other is the rest. And that actually is a beautiful theory that can be done. It's a beautiful piece of geometry that I think Jason Starr discussed fairly thoroughly last week, but I'll review it anyway. So we define, first of all, a smooth, so the type of big pieces is the following. A smooth projective variety P is said to be rationally connected if through any 2 points in P there is well, basically what I'm trying to say is that I can draw a rational curve through any 2 points. The reason I say there is a map is because if the curve is if P itself is a rational curve, what does it mean to draw a rational curve on a rational curve? I mean, you can, if P is a point is considered rationally connected, so you can't draw a rational curve on the point. Okay, so this is the picture. So this is rational. And Jason, I'm sure, mentioned quite a few equivalent definitions for a smooth variety to be rationally connected. This is actually what's not evident from this definition, that this is actually an equivalence relation. If you have 3 points, well, all you see is just 2 rational curves, a chain of rational curves. But in fact, once a variety is rational connected, then any chain of rational curve can be kind of pushed a little bit and smoothed out. This is really a beautiful piece of theory, which I don't know if Jason had time to discuss in detail. Also, there's a completely geometric condition which says that there is a rational curve in there whose normal bundle is ample. So it can be moved in any way. So that's a completely infinitesimal situation. Only nearby a single rational curve, and yet it's enough. Also, Jason must have told you that this is a really nice property. It's stable under birational equivalence. It's stable under degenerations. If you have a family of rationally connected, both degenerations and deformation, if you have a family of rationally connected varieties, and one, which is a smooth family, if you have a family of variety, a smooth family, if one fiber is rationally connected, then the other is rationally connected. And so on and so forth. This is really a nice class of varieties. The only rationally connected surfaces are rational. So for surfaces, it's a boring condition. But already for threefolds, it's interesting. Okay. so I said that I want to use this to break a variety into pieces, and that still, I'm sure, this is something that Jason mentioned, because this is one of his most spectacular results. So I should just say that this is, I combined here two theorems. And again, I will need to draw a picture on the board. So why don't I draw the picture first? So if you have any variety x, then what you can do is, at least up to birational equivalence, so let's ignore this birational equivalence x prime to x. I already replaced x by something birational to it. There's a well-defined map, x to z, such that the fibers collect everything that has to do with rational curves. So the fibers, so the generic fiber, in fact, what I said is if you have a fiber which is rationally connected, then all smooth fibers are. So that it's enough. So you have a fibration, so let's ignore the x prime to x, such that the general fiber or generic fiber, doesn't matter, is rationally connected. So the fibers are rationally connected varieties. So here's z, here's x. Everything in here, every 2 points in here can be connected by rational curves. And on the other hand, on z itself, I don't see almost, well, there might be some rational curves, but they are not everywhere. Z is not covered by rational curve, is not uniruled. So everything that can be sort of connected by rational curves is already in the fibers of this map. So this is exactly what it says here. The general fiber is rationally connected, and Z is not uniruled. Let's ignore this part for the time being. You can see that in the notes. This is just to... The rational map that you have here, so this is only a rational map, is called the MRC fibration, the maximal rationally connected fibration of X, and Z of X is called the MRC quotient of X. Or I think Jason might have called it the rational quotient, but it's not rational, so I don't like it. It's the opposite of rational. The MRC fibration, just the way it's written as a universal property, it's the final dominant rational map with rationally connected fibration, fibers. So if you have any map X to W where the fibers are rationally connected, then it factors like then the MRC fibration factors like this. So it collects all the rational connected stuff in fibers in one piece. What I want to do. So now I want to tie this. So every variety can be broken into the thing that has to do with rational curves and the rest. And since we have an idea of what arithmetic should be on rational curves, we can conjecture that this can actually work in higher dimension for the analogous thing. So the conjecture, which I think the only place where I've seen it stated as a conjecture is in Campana's papers, although other people have definitely worked on something like this. Conjecture says that if P is a rationally connected variety over a number field, then rational points are potentially dense. So at least after extending the number field by a finite amount, so there exists well, L over K finite, such that P of L is dense in P. This is known for if you replace K by a number field, there's a stronger result that is known for a function field of a curve of an algebraically closed field. Then, in fact, the rational points are dense. You don't need an extension for such a field. Okay. And you can view some of the stuff that Yuri Chinkel told you about as going in the direction of understanding the conjecture and understanding it even better. All right. I want to remove this. So one piece of varieties is going to be rationally connected varieties. Now suppose that we don't have a rationally connected vibration on a variety X, then what does it say? It says, well, at least conjecturally, so the rationally connected vibration is trivial, which means that X is not uniruled. And conjecturally, a non-uniruled variety, by the conjecture I mentioned before, by the minus infinity conjecture, has differential form. So its Kodaira dimension is bigger or equal to 0. And if its Kodaira dimension is bigger or equal to 0, then you can take the differential forms and use the map defined by these differential forms, which I call the Ithaka vibration. X goes to I of X. Maybe I should have written it. So I of X is defined by the spaces of sufficiently high pluricanonical differential forms. And it's so one thing that is not difficult to show is that the fibers of this are always of Kodaira dimension 0. So you don't need any fancy additivity results. It's almost automatic to show that from the vibration inequality, the easy additivity, that subadditivity, that the fibers have to have Kodaira dimension 0. Okay, so this is very much like an elliptic vibration. And on elliptic vibration, we also know that we have lots of rational points. So here's a here's a conjecture of Campana, which says that, sorry, not on elliptic curves we have lots of rational points. So Campana looks at the fibers of the Ithaka vibration, namely those varieties which are of Kodaira dimension 0, and he conjectures that if F is a variety of Kodaira dimension 0, then rational points are potentially dense. And really, there are dozens of papers now by Hassett and Chinkel and Bogomolov and Harris and Kolyot-Helen and many people trying to give examples of that this is actually true. Trying to construct points on such varieties. It's not always easy. So these two conjectures are conjectures about existence of rational points, of lots of rational points, at least after extensions of the number field on varieties of Kodaira dimension, on either rationally connected varieties or Kodaira dimension 0 varieties, which are sort of building blocks. You start with your variety, you take the maximal rational connected variety, you get something which is of non-negative Kodaira dimension, so it has an Ithaka vibration. That's the next piece sort of the variety. You can try to break it up further. And that's something I will try to do. In a bit. I think Hassett gave you a number of examples of this for surfaces, right? For rational points on certain K3 surfaces, or? Oh, okay. But we did talk about rational points on surfaces. So let's look at the other extreme. Those varieties that are in the zoo, that are the analog of curves of curves of genus bigger than 1. And here we have a conjecture, a very inspiring conjecture, which says, well, this is Lang's conjecture in weak form. Suppose X over a number field is a smooth projective variety. In fact, it could be just any field which is finally generated over Q. It doesn't need to be a number field, but number fields are good enough. Then the rational points are not Zariski dense in X. So Lang conjectures that if you throw away a closed subset, you won't find any rational points on your variety, if the variety is of general type. And in fact, motivated by other types of geometry, which I will not discuss here, Lang was a conjecture what kind of closed variety you have to throw away so that all you'll find once you throw that away are just sporadic rational points that you have to construct one by one. And so the conjecture, so there's a geometric conjecture that says that if X is a smooth projective variety of general type, then you can try to collect all the subvarieties which are not of general type. And theoretically, they could be a countable collection of which might be dense of subvarieties. And Lang says that no, it's not so wild. He conjectures that there is a Zariski closed proper subset S of X whose irreducible components are not of general type, so these are the pieces of S of X, and such that every subset which is any other subvariety which is not of general type, subvariety, is actually contained in this S of X. So Lang conjecture that there's kind of a non-general type locus which contains everything that is not of general type. Okay? No, it does not depend on anything. It's a geometric thing. And here's what is its arithmetic consequence is what we call Lang's conjecture in strong form, which says that assume that geometric conjecture holds, that let X be any smooth projective variety of general type over a finitely generated field, then for any field, for any such field, the number of rational points away from S of X is finite. So of course you can, by extending the field, you can construct a rational point here, a rational point here, but what the conjecture says is that you can't get a big collection away from S of X. So notice the difference between finite and Zariski dense in the weak form, and non-Zariski dense in the weak form. So this actually says where the possible density can occur, only inside S of X. One small application of the weak form of Lang's conjecture. Assume that the weak Lang conjecture holds, then assume that you have a variety defined over a number field. Assume that there is a dominant rational map from X to a variety of general type. Well, Lang says that the rational points here are not dense. But any rational point here will map to a rational point here, at least where the rational map is defined. So let's throw away the closed subset where the rational map is not defined. Then then rational points here cannot be dense because this is a dominant rational map. So any rational map here has to map to the closed subset, and the inverse of a closed subset here, because this is a dominant map, is a proper closed subset. Okay? So if it maps to a variety of general type, then according to Lang, rational points cannot be dense. So we'll see how to apply this. So this is Lang's conjecture. I think Yuri is not here, and so if you asked Yuri, he would say this can't be true. But really, okay. So here's one reason why people would say this can't be true. There's the following consequence of Lang's conjecture. So you can apply Lang's conjecture to judiciously chosen varieties. One judiciously chosen variety is the moduli space of curves or curves with a number of points on them. And if you apply it carefully, you get the following theorem, which is due to Caporaso, Harris, and Mazur. And the theorem says that if the weak Lang conjecture holds, and if you have a number field K, I guess I should use this rather than point on my transparencies. You have a number field K, and you fix a genus of curves bigger than 1, then there's a uniform bound on the number of points on all curves over that same number field of the same genus. So there is a bound nkg, so that for every genus G curve, the number of points over that field is not more than this bound. Now this is quite a bit more than people expected before. And it's a wonderful consequence of a nice geometric conjecture. You conjecture something about higher dimensional variety, you get something wonderful about curves. Here's a refinement due to a student of mine, Patricia Pacelli. The refinement says that, in fact, this bound depends only on the degree of the number field. You still have to take points over a fixed number field, but it's, the number of points is bounded only in terms of the degree of the number field. You can ask what happens if you assume strong Lang's conjecture, and this really throws people off. Assume that strong. So this is again a Caporaso-Harris-Mazur theorem. Assume strong Lang and fix a genus. Then there is a uniform bound on a number of points on almost all curves. So let's read it. You have to think about it. There's a bound depending only on the genus, such that for any field K, the number of rational points is not more than G. This, without a caveat, this is nonsense. But this is only true for all but finitely many genus G curves C over K. So for any field, any arithmetic field, I should be able to write down a finite collection of curves, kind of offending curves, such that for all other curves, the number of points is bounded by this n. Really, really wonderful. But there's a good number of people say Lang's conjecture cannot be true. But you know what? I don't care. Because let me just, yeah, okay, go ahead. Okay, so if you look at, if you collect all degree D points on a curve, then you can have curves with many degree D. You can always take a curve which has, of any genus which is a D-fold cover of P1.
Okay, so can you make some exclude those?
Okay, you can try pushing the envelope, but there's only so far that you can. I mean, there are results in that direction, and there are results that actually follow from Faltings's theorem if you don't go too far. But let's leave it. I mean, there's a lot of inspiring ideas that you can bring. So let me just, so this is just a point made by my colleague Joe Silverman, which says, well, maybe I need the whole board. And the point is that even if you don't believe Lang's conjecture, it's something that is worth studying, understanding. I mean, it's not the end. Even if it's not true, if it were not, depending on the day of the week, I might think that it's true or not. But even if it happens not to be true, what do we have? So we know that on Pn, the number of, or P1, the rational points, number of rational points grows polynomially in terms of a bound on a height. So this is something that Yuri showed you. On abelian varieties and stuff like that, the rational points grow logarithmically. So this looks more like this. And what Lang's conjecture says is that let me try to be careful. So what Lang's conjecture says that on varieties of general type, it looks more like this. But what Silverman says, you can say that this is a constant. But what Silverman says that for the naked eye, so if this is B or polynomial in B, and this is a polynomial in log B, for naked eye, this is just log B is a constant function for any practical purposes. So maybe that's the way rational points on a variety of general type behave. Anyway, let's leave it as that. So we have conjectures about having a lot of rational points on varieties which are rationally connected or Kodaira dimension 0. We have conjectures about having few rational points on varieties which are of general type, and we want to know what happens in between. And that's basically what I want to cover the rest of today and tomorrow, and maybe continue, depending. I mean, that's kind of the center point of what I want to tell you. We want to search. Remember what I said in the beginning, geometry determines arithmetic, at least after you throw away the randomness. You want to have some invariants that will tell you what the general arithmetic behavior of a variety will be. So this is something I stole from a lecture of Caporaso, which is on the web page, on my web page, which just investigates a little more in detail the situation of surfaces. And I bet Brandon told you something about this. So here is what Lang conjecture says, and we know many examples of, quite a number of examples, maybe not many, of surfaces of Kodaira dimension 0 which have few rational points, non-dense rational points. We don't know any counterexample to Lang's conjecture. As to Campana's conjecture, we know by now many examples that Brandon and Yuri and others have worked on of surfaces of Kodaira dimension 0 that have a potentially dense rational points. So any product of two elliptic curves or any abelian variety, abelian surface, but many others, many K3 surfaces and so on, that we know have potentially dense rational points. We don't know an example of a counterexample to Campana's conjecture. In the Kodaira dimension minus infinity case, we have a complete dichotomy just like in curves. If you have a rational surface, then it has a lot of rational points. And if you have something that is birational to P1 cross a curve of genus bigger than 1, then then rational points cannot be dense because they have to map to rational points on the curve. We have a similar case here in Kodaira dimension 1. There are many examples, and I'll give you one, of surfaces of Kodaira dimension 1 which have potentially dense rational points. There are also these examples, and I'll give you more than this, of surfaces which do not, because they map to curves of a genus bigger than 1. So this is just what I said here. So we definitely understand what's happening here. The understanding of what's happening here is that I've given you so far is not complete yet. So we still have to do something about Kodaira dimension 1. One thing you immediately see here is that the Diophantine geometry of a variety is not governed by the Kodaira dimension. The two lines here, minus infinity and 1, show that you can have the same Kodaira dimension but very different arithmetic behavior. Yes, Owen? I will get to that. Yeah, I will get to that. It's not me who has the example, it's somebody else, but yeah. So I want to give you two examples of surfaces of Kodaira dimension 1, which exactly brings up, the second one brings up this point. So first of all, I want to give you an example here that really you can have a lot of rational points on the surface of Kodaira dimension 1. And I should draw pictures on the board. I'm probably driving the person taking the video crazy because I'm using that projector and this board, but so the idea is as follows. You take P2, and you take two cubic curves, and everything should be defined over Q, and you can take the cubic curves to pass through two rational points. You can make these rational points to be non-torsion, so that the difference is non-torsion on any one of these two cubic curves, two elliptic curves. So the total space of the family of cubic curves that you get is an elliptic surface, fiber by P1, which is just a blow-up of P2 at these 9 points. The total space of the pencil is the blow-up of the family of curves of P2 at the base points of the pencil. So in fact, you have not just two sections coming from these 2 points. You have 9 sections, and you have more because I assume that the difference here was not torsion. And of course, you have a number of, have exactly 12 singular fibers, but we don't worry about those for the time being. Next, what you do, so this is rational. This is not Kodaira dimension 1. But you can take a base change by the map that is described there. You take a base change by taking a kth root of the parameter t here. So s to the power k equals t. And in order for the example to work, you need the k to be at least 3. And what happens is you just pull back, and you calculate, and this is one of the exercises in the notes, you calculate the Kodaira dimension of this. The Kodaira dimension of this is 1. So this is the surface S1, and KS1 is 1. This is a classical and important calculation that every student should do. But what do we have on this? We still have the pullback of these two sections. We have more sections. And these are non-torsion. Then you can do the following. Take any rational point on P1. The fiber is an elliptic curve. over the rational. It has these 2 points, but these 2 points, if this is the origin, then this is not a torsion point, so you have infinitely many points on this elliptic curve. And that happens for almost all. So it happens for all points where all rational points where this misses the major torsion points. So almost everywhere, these are going to be, the restriction of this non-torsion section is going to be non-torsion. So we'll have infinitely many points on infinitely fibers. So there are x of k. In fact, x of q is dense in this particular example. But example 2 is on the other side, and that brings about the question that Henri, once you see that Kodaira dimension is not good enough, in the example I wrote there, it seemed like all you need to check whether the rational points are dense or not is whether or not there's a map to a variety of general type, a dominant map to a variety of general type. This shows that this is not the case. So existence of maps of variety of general type is not enough to say whether or not you have dense rational points. So here's a variety which does not have any map to a variety of general type. Here's a surface that does not have any map to a variety of general type. To a surface or is not of general type, does not map to a curve of genus bigger than 1, yet the points are not dense. And this is again a Chevalier-Weil argument, just like Henri has shown you last week. So suppose C is a hyperelliptic curve. This is another picture of. So C is a hyperelliptic curve, and E is an elliptic curve. So C being hyperelliptic, it has an involution. I can also cook E to have an involution, but a fixed point free involution, namely translation by a 2 torsion point. So I'm assuming that E has a 2 torsion point. What did I call it? A? Call it there A. And therefore, the product surface has an involution described there. X, Y goes to, so on E I add the torsion point, and on C I do the involution, the hyperelliptic involution. That's a fixed point free involution because it's already fixed point free on E. So I have the map from, so this is Y. And I have this involution phi tilde on Y. So I have an étale map from Y to another surface, and this surface does not map to C, but it maps to the quotient of C by the involution, namely P1. So this is S2, which is the quotient of Y by phi tilde. And an easy argument, which I skipped, it's in your notes, it says that if you have an étale cover, then the Kodaira dimension is the same. A finite étale cover, Kodaira dimension is the same. So the Kodaira dimension of S2 is the Kodaira dimension of E cross C, which is 1. On the other hand, and also S2 of K is not dense by Chevalier-Weil. It has an étale cover by something where the rational points are not dense. Chevalier-Weil and Faltings, where the rational points are not dense because it's a big theorem. But S2 does not have any map to a Faltings curve, to a curve of genus bigger than 1. Because if you had one, then it would have to be either E or an image of C, and the only thing that C maps to in this picture is P1. So it does map to E, but it does not map to C. So that answers your question. So life is more complicated. You still argue in Faltings. And the topic of the next lecture will exactly be how to understand what's in between general type and Kodaira dimension 0. But I want you to remember these 2 examples because they are going to come up. I don't think I will start lecture 2 today, but maybe I will. Let me just make a very quick discussion of the open case. I only discussed proper varieties so far, just in analogy, and the analogy is important for me for what will come up later. I want to discuss the open case. I want to understand integral points on open varieties. So just as for curves, on open varieties, the natural thing to study is integral point. I take a smooth projective variety x bar with a reduced normal crossing divisors on x bar called D, and I call x the complement. And the notation differs in the literature, so you might find other notations for maybe k bar of x is the Kodaira dimension. So this is the logarithmic Kodaira dimension of x, or k log of x, is the Kodaira is the Itaka dimension of x bar with a divisor class kx bar plus d. So you throw in the boundary divisor, so to speak. It is important, though, that the boundary divisor has to have nice singularity. So reduced normal crossing is the analog of for the open thing. I want smooth. Okay, so it's kind of as good as it gets. So I'm not sure what the common notation is. There are more than one notation in the literature. An easy exercise is that this number is independent of the completion. We say that x is of logarithmic general type if this logarithmic Kodaira dimension is the dimension of x. And we have an analog of Lang's conjecture, which is the following. Remember that I need to work with integral points, and integral points live on integral models. So I have to spread out my variety over a ring of integers. So suppose x is a model of x, script x is a model of x over the ring of s integers of the number field, and then I define s integral points in the usual way, just schematic points of this scheme script x. And the Lang-Voita conjecture says that if the variety itself is of logarithmic general type, then nth integral points are not Zariski dense. This is in direct analogy with a table I had for you in the end of the first of lecture 0. Where is this? I'm going to suffer for this. This is the table I had for curves. Table I had for curves which said that if a curve is of logarithmic general type, there are only finitely many points. That is a theorem. In higher dimension, it's conjectured. And that's the Lang-Voita conjecture. It's part of a more refined conjecture of Voita that has to do with heights, and I might get to it in the very last day of this course. I said that I'm going to be in trouble for doing this. All right. So you can imagine that just as the Lang conjecture has wonderful implications for curves, there are wonderful implications even for elliptic curves by the Lang-Voita conjecture, which says something about finiteness of a certain type of integral points in a uniform way. You have to be careful. You have to take integral points on semi-stable models for this to work out. And just as before, even though the conjecture is very inspiring, you ask yourself whether you can believe the conjecture if it has such wonderful results. The conjecture in particular, if you take the case where x equals x bar and D is empty, then that's you get back your Lang conjecture. So the conjecture is a generalization of Lang's conjecture. Or if you insist on, well, remember that Siegel. Okay, so there's an accident with curves, which is that any open curve is affine. But you can ask what happens when the only cases that are known are well, almost the only cases that are known. There are two types of cases that are known. One case that is known, or kind of general cases. One case is subvarieties of semi-abelian varieties. Everything is known there due to Faltings and others. Another is the case of the moduli space of abelian varieties, which is an open variety for which I mean, basically Shafarevich conjecture is a statement about the moduli space of abelian varieties. Well, only the cases of this conjecture that are amenable to taking covers, and in higher dimensions, well, you don't have as much freedom to work with fundamental groups and cook up covers. So it's not completely general. The Faltings implies Siegel does help you in some cases, but not in general. This is something I should have put. Okay. So in the next 2 minutes, I want to just philosophize a bit about what's coming. And what's coming is Campana's program, whose goal is exactly to understand what comes in between. You're surprised that your name is appearing here, right? What comes in between Kodaira dimension 0 and general type. There are all sorts of varieties that occur there, and you want to understand when you could imagine that the variety would have a dense collection of rational points and when it doesn't. And here's a little bit of background. So the idea, so as Henri asked whether it's enough to just look at maps to varieties of general type, and the answer was no by the example S2. But you can, what Campana comes to show us that maybe there's something else. So instead of looking at maps to varieties of general type, you look at maps to dragons of general type, and that's good enough. And these dragons are what Campana calls obifolds, and I don't like it because it's misleading. I call them Campana constellations. Okay, so you should be forewarned that this is not a universally accepted terminology, although I asked Campana about the word constellation, and he actually loves it. So it depends whether or not it will catch. And I think it makes sense, the picture that you see. So let's go back to where we what we had. We had two examples still on the board of S1 and S2 with Kodaira dimension 1. But they had the same Kodaira dimension, but the arithmetic behavior was vastly different. And Campana's question is there an underlying structure on the base P1 in both cases that distinguishes between the two cases? In this particular situation, in this particular example, and almost completely in general for surfaces, there is an old structure that we can use. And the old structure is truly called orbifolds. The key point is that S2 was obtained as a quotient of E cross a hyperelliptic curve by an involution, and on that involution on the hyperelliptic curve had 2G plus 2 fixed points, So if you think about the inverse images here, what you get as a fiber here is the quotient of the elliptic curve by the two-torsion translation. And this means that the fiber is a double fiber. So in fact, you have 2G plus 2 double fibers on S2, namely that 2G plus 2 points on P1, which are kind of weird points, where something happens on the fiber. And, I see why okay, so the name, your name will appear here. So in fact, the map from S2 to P1 is not just a map to P1 itself, but to P1 with extra structure, a structure that we call an algebraic stack or orbifold, which is obtained by locally taking a root of the equation of the divisor of these two G2 plus 2 points. So there's an extra structure which is called an orbifold structure. I will not discuss it in detail because I'll discuss something else that happens more generally. An orbifold structure on P1 obtained by taking a square root of the defining equation. And this is something that was discussed in a paper of Darmon-Granville. And the beautiful thing, it's a beautiful paper. Oh, it was a lecture. One of the beautiful things there is the title of that paper. I love this. It doesn't actually tell you that they go out and develop a theory there. The title is, on the equations, x to the p plus y to the p equals something and something else. Very explicit. But they consider, so what you consider is the canonical sheaf of this orbifold. And the point is that the canonical sheaf of the orbifold is not just the canonical sheaf of P1, but you have to add 1/2 of this divisor D. The correct formula is 1 minus 1/2. But so